Okay, good morning. Happy Friday the 13th. Today, we have our very last section of new material. We're going to talk about growth and decay, that is word problems that result in differential equations. Project number 9 I handed out last time. Is there anybody who didn't get one last time? Okay, so that is due at the start of the final exam. I'm going to hand you the 6th and final take-home quiz. That will be due on Monday at the start of class. And Monday is our review day for the final exam. We'll just, again, talk very briefly in the first few minutes of class generally about the exam, and then you'll study for the hour and 10 minutes. Another reminder, we're going to start our class on Monday early. Instead of 10:40, we're going to start at 10. Same hour and 10 minutes, just shifted ahead a little bit. So thank you for working with me on my new schedule here. And then our final exam is Wednesday coming up, 10:30. Questions on the calendar?
Is there a way we can find out our final grade?
Yeah, you can email me after you take the final. Email me from your GCC address, not, cutie-pie84 at Gmail. I just guessed.
Should we give you like 5 days a week to email you?
You can email me as soon as you walk out the door. Okay. All right. No, but you can email me. All right, here we go. At the top of page 84, in this section, we tackle some word problems. We'll call them story opportunities that involve differential equations. Number 1, lots of things grow or decay at a rate proportional to their amount of size, leading to differential equations of the form dy dt equals k, some constant times y. So we've seen these before. Rate of change is proportional, constant multiplier times the original population, which is y. We could generalize further and assume that a constant amount is added or subtracted from the population each period. So we're still gaining a certain percentage of the population, but additionally, there's like an external increase or decrease by some constant amount every time. And so that leads to slightly more general differential equations of this form. And we're going to talk about some of those today. So number 2. For example, a scholarship fund earns continuous interest at a rate of 8% of the current balance per year, and $1,000 is withdrawn each year in a continuous way. So we're just imagining we've got this scholarship that we've won, and it's in the bank, and it's earning 8% a year, but we are taking out $1,000 per year, right? So we've got interest, so our amount is going up, but we're taking out 1,000, so the amount is going down. Let's see if we can write a differential equation that represents this situation. In this case, y is equal to the amount of money in the account, or the value of the scholarship at time t, which is in years. And so let's just translate into a differential equation. dy dt represents the rate at which the value of the account is changing. It's changing for two reasons. There's interest, and there's the withdrawal of $1,000. So the interest is 8% of the current balance. So 8% times y, right? That is the current balance. It's changing, but we're calling it y. That's a growth, right? We're gaining money from the interest, but then we are losing $1,000 per year. So minus 1,000. Don't even need to put a t in there, I don't think. This is just $1,000. The 8% is a per year interest rate. That $1,000 is a per year withdrawal. It's just straight up $1,000. It's being withdrawn in a continuous way. It's like you're withdrawing fractions of pennies every moment of the day. So it's not at discrete moments of time. It's not once at the end of the year. It's all the time. The money is growing slightly by 8% and falling slightly by little parts of the $1,000. Questions on that? Okay. So we could solve that differential equation. I don't think we're going to today, but we can easily find this thing in number 3. In the last scenario, how much money would need to be in the account for the amount to be stable? So stable means not changing. Means the derivative is supposed to be what number? 0, right? That's how we're going to make the amount of money stay constant, is by having a derivative equal to 0. So we're just going to solve the equation. 0.08y minus 1,000 equals 0, right? Just change the derivative to a 0. And what do we get here? Somebody help me out. Is it 12,500?
Yeah.
So what does it mean? It means if the initial amount of money in this scholarship fund is $12,500, then it's going to gain 8% a year, and we're going to subtract $1,000 a year, and what's going to happen at the end of a year? It's going to be at 12,500. In fact, it's going to be at 12,500 at every second, because we've got this 8% coming in, which is perfectly balanced by the 1,000 coming out, well, fractions of the money coming out. Okay? And so y equals 12,500 is called an equilibrium solution. If you are there, you will stay there forever and ever and ever. What do you think? If you start with more than 12,500, what's going to be the long-term behavior of the amount of money in the account? It's going to grow. How big? Infinity. If you're more than 12,500, the 8% interest is more than the $1,000 that's coming out. So every year you're going to have more than you had the previous year. It's going to grow. If you start with less than 12,500, then eventually zero, because the $1,000 is more than the 8%. If you have exactly 12,500, the $1,000 is equal to the 8%. Perfectly balanced, stays static. Okay, let's try number 4 here. It says dead leaves accumulate on the ground in a forest at a rate of 3 grams of leaves per square centimeter of ground. So leaves are just falling on the ground. Depending on how many square centimeters of area you have down there, you get 3 grams of dead leaves falling per square centimeter, and then that's per year. Every year we've got this 3 grams per square centimeter, and at the same time, so we have the leaves falling, but the leaves that are on the ground start to decompose as soon as they hit the ground, right? Probably start to decompose while they're still attached to the tree. And the continuous rate of leaf decomposition, they're saying, is 75% per year. So let's see if we can do the same thing where we write down a differential equation that models not how much money is in the bank account, but how many grams of leaves are on the ground. So let's try. Okay, so Q, it says, is the quantity of leaves. So let's write our differential equation. dq dt equals, so this is the rate of change of number of grams of leaves, and it's changing for 2 reasons. Leaves are falling and leaves are decaying. So the falling leaves is 3. Is it a positive 3 or a negative 3? Positive 3. We are gaining 3 grams of leaves per square centimeter, just like we were subtracting $1,000 on the scholarship example. They are decomposing at a rate of 75%. 75% of what? Of Q, whatever is there, 75%. So actually, I'm not sure from this question. Do you think it's 25% or do you think it's 75% there? They decompose.
How much is left, right?
Yeah, 0.25 would be what's left. So that's not what we want. We want 75%.
We want negative 7.
Indeed, that is what we want. Thank you. Negative 0.75. All right, I feel good about that. I wasn't sure about the 25%, but this is the rate at which the amount of leaves is changing. It is changing by 75% because of that decay. Okay. Alrighty, let's do part B here, equilibrium solution. Can you guys find it with your neighbors? So you're solving an equation. Even if you can solve that equation in your head, go ahead and write the equation down just to make sure you're clear. Equilibrium solutions are always found in the same way. What are we changing in our differential equation to find the equilibrium? Q dt becomes 0. There we go. And so Q is 4. So if it happens that you have exactly 4 grams of leaves per square centimeter on your forest floor, then it will stay at 4 grams per square centimeter. Right? The amount of leaves falling is going to be perfectly balanced by the decay of the leaves that are on the ground. Okay, let's go ahead and solve this differential equation. We'll try to do this kind of quick here. So going back up to this guy, pretty much the only technique we have is separation of variables. So we're hoping to get what variable to the left?
Q on the left.
Q on the left, T on the right. The only thing we're allowed to do is multiply and divide, no adding and subtracting. So what are we going to divide both sides by? The whole thing. We cannot just move the Q, we got to move the whole thing. So dq over the entire thing, negative 0.75 Q plus 3 equals, and then we move the dt over to the other side. There was an invisible 1 was the only thing left on the right-hand side. So that's it. And the reason dividing by Q is not going to cut it for us here, it's legal to do so, and you can divide by Q, but when you divide by Q, you got to divide everything by Q. So even though dividing by Q gets rid of that guy, there's still a Q on the right-hand side. And so we haven't moved all the Qs to the left-hand side. You could do that. You can factor out the negative 0.75. There's something to be said for that. And it's actually going to make the differential, the integral we're about to do easier if the negative 0.75 were on the right and not the left. So I like that strategy. It should work. Okay, so let's give this a shot. In front of each side, we put our integral symbol. Okay. Again, since I'm the teacher, I'll go ahead and do the hard one. So that's t plus the constant. Leave my students with the easier one. I'll say I never did nothing for you guys. All right, so left-hand side, what is it going to become with a suitable u substitution? It's going to be an ln, so I'm going to put the ln here, negative 0.75 q plus 3. But we do have to pay for the u substitution. We're not going to do all the details here, but you can check later. That negative 0.75 as a derivative ends up getting flipped over by the u substitution process. So that's a negative 3/4, so negative 4/3, which I'll just say, you got to do the details if you want to see where that came from. Okay, let's go ahead and solve for what letter? Q. If possible, we solve for the dependent variable. It's Q in this case. So we'll move the negative 4/3 over. So we go ln of negative 0.75 Q plus 3 equals, so I'm multiplying both sides now by negative 3/4. Did you do the u substitution?
Sort of half.
So yeah, so it's on the bottom, right?
Right.
Yeah, and so 1 over, and it flips. I mean,
Can't you just keep it on the bottom?
But it's not on the bottom the way you've written it. Yeah. Okay. Still solving for Q, but we're gonna start to clean up the constant business here, and this is something that trips up a lot of students when they're first starting to play with this plus C stuff. I'm going to go ahead and distribute the negative 3/4 here. But negative 3/4 of a constant is just a constant. And so I'm just going to call it plus C. I mean, you're welcome to put minus 3/4 C, but there's no reason to hold on to the, the transformations of the constant. If it's just a constant, it's simpler to just call it C. So copying the left-hand side here. And then we'll hit both sides with an E. So left-hand side is just negative 0.75 Q plus 3. Right-hand side is E to all of this stuff. And now a really useful and really common, constant transformation technique is right here. If we split this right-hand side up as e to the negative 3/4 t times e to the c, everybody buy it? Right, because if we started with this, yeah, like we agree these two things are equal here? Yes, because we would keep the base and add the powers, which is where it came from. And then e to a constant is just a constant. So how about we just call that whole thing e to the negative 3/4 t times constant. You don't, I mean, we technically we should have. The C has changed twice from the original C that it was. So if you still have 3/4 on it, it's fine. But it would. So if you still had the 3/4 on the C, then the value of C that you get would be different than the value of C that I'm going to get. But ultimately, after you multiply your C by -3/4, it's going to become the C that I have. Yeah. Okay, just 2 more steps to solve for Q. So we're going to subtract the 3 and then divide by the -0.75. So we'll do both of those in one shot here. Q equals constant e to the -3/4 t, subtract the 3, divide by -0.75. And then let's clean this up. It's not so common to have a fraction where there's decimals inside of it. Right? Let's just pick either decimals or fractions. Let's pick fractions. Equals -0.75, that's -3/4. If it's on the bottom, then what can we do to make it on the top? 4/3, right? So 4/3 times all of this stuff. -4/3, thank you, times all of that stuff. And then finally, we'll distribute that -4/3 through, and it's going to be as clean as it could possibly be. ln was negative, yeah. Okay, so we'll distribute that -4/3 through. Our final abuse of this poor letter C, -4/3 times a constant is a constant. So C e to the -3/4 t, and then -4/3 distributing to the -3 becomes +4. Fantastic. Distributing the -4/3 to the -3. What a lot of calculus students are dismayed to discover is that in these problems, the calculus is like 10%, and then the algebra and pre-calc is like 90%. Like it's just a lot more work to do this rewriting for Q than the actual antiderivatives. The antiderivatives were pretty easy, but it is what it is. That's why there are a lot of prerequisites for this course. Okay, so that's our solution there. On the next page, we'll solve for a particular value of C, but before we do, can you guys, so what did we say about our equilibrium was it 4, right? So what does that mean? So if the Q were equal to 4, yeah, so if the Q is equal to 4, like if I just change the Q to a constant 4, that's what we said the equilibrium was, then what does that mean the C has to be? 0. And if the C is 0, then we don't have any of this exponential growth or decay stuff happening, right? It's just constantly 4. Other thing I want to say, if you start with something, so if C turns out to be, well, actually it doesn't matter. Suppose that t goes to infinity. This whole formula, it's been Q of t the whole time. If t goes to infinity, e to the -3/4 of infinity, what does that approach? 0, right? And so it doesn't make any difference what the constant c is. This whole c e to that term approaches 0, so the whole thing approaches 4, right? That +4 that's sitting over there. So what does it mean? In this case, if you start with more than 4 grams of leaves per square centimeter, what are you going to head towards? 4. So like if we start with 100 grams, lots and lots of dead leaves on the floor, they'll still fall at, what was the rate? I think it was 3 grams was the fall rate, but you lose 75% of this massive amount of leaf stuff on the floor, and eventually it's going to level off and head you down towards 4 grams per square centimeter. If you start with not very many leaves on the floor, like 1 gram per square centimeter, what's the long-term behavior here? Still going to 4, but now we're going up to 4. The rate at which the leaves are falling is going to exceed the decay, the leaves that we're losing here. So in both cases, we're heading towards 4. It's kind of like that, we talked about that skydiving thing with the terminal velocity was our equilibrium. The poor guy shot out of the plane faster than terminal velocity, right? But heading towards that terminal velocity. Same idea here. Notice that this is a really different behavior than the money example. Remember the money example, 12,500 was our equilibrium. If you start with a penny more than that, then what's the long-term behavior for the amount of money in the account? It goes to infinity. If you start with a penny less than 12,500, it goes to 0. So in both cases, we've got this equilibrium. Just imagine this horizontal asymptote. In this case, all roads lead to 4 grams per square centimeter, right? From above or from below. But in the money example, all roads lead away from 12,500, from above or below. It's a really, really different behavior, even though, you know, it's still the same horizontal equilibrium solution in both cases. Okay, part D, suppose the quantity of leaves at time t equals 0 is 10 grams per square centimeter. Let's find the particular solution. So I'm just going to rewrite our formula from the previous page, c e to the negative 3/4 t plus 4. Changing t to 0, changing q to 10. So 10 equals c e to the negative 3/4 0 plus 4. How much is c? 6, right? Because that e to the 0 part is 1. And make sure after you find the c, finding c is not the last thing you write. The last thing you write is the copy of the solution, but you change the c to what you just found. So our answer here is q equals 6 e to the negative 3/4 t plus 4. Trevor. Correct. Also pointing out, Ben had said, you know, what happened to the 3/4? It should be attached to the c. So imagine, you know, I mean, like the c that you might have found if we hadn't changed c 3 different times would be a very complicated expression, right? And if you eventually do all the distributing, you'll come around to this exact equation. But I just think it's, if you can make c simple along the way, you should do it. Okay, and then finally part E should be pretty easy. It says use the particular solution to predict the quantity of leaves on the forest floor after 3 years. So all we're doing is changing t to 3, and that's it. So q of 3 is what we're after. 6e to the negative 3/4 times 3 plus 4. All right, I'm gonna make my guess here, and I'm recording this. This is gonna be captured forever. I'm gonna say like 4.6. What do we have? 4.63. Take that, YouTube. 4.63 grams per square centimeter. Well, you'll have to trust that I didn't do this calculation ahead of time and came in prepared, which I didn't. I honestly haven't looked at this problem in roughly 12 months from now. But I don't know. And this lecture actually sometimes gets snowed out, so I don't even get to do this one every year. But it's been a while. You should be impressed, is what I'm saying. Okay, activities are right down here. Again, if you came in late, there is an important typo we need to fix. In the parentheses, that needs to be a capital T, not a lowercase t. One last thing I'm going to add about this Newton's law of cooling problem that you're about to solve is that in all of the differential equations we've solved so far, there has been a single constant to be found, c. In this problem, there are going to be 2. One of them is k. It's a constant that's just part of the formula. And at some point down the road, you're going to do an integral, which leads you to bring in a plus c. So you're going to have to find the k and the plus c, which means you need 2 initial conditions. So it says, you know, temperature is, where is it? temperature is lasagna is taken from the fridge. So it starts at 40 degrees, and then 1 hour later, it's 90 degrees. So we got to give you two pieces of info so that you can find our two constants. I'll walk around. I expect we'll run into some difficulties as we solve, but let's give it a shot.